Hi everyone, this is Mrs. GA, and today we're going to learn about exponential functions. But first I have a quick warm-up for you guys, so please pause the video and give this a try, and when you're ready to check, just hit play. Alright, so go ahead and check your work here. I think the tricky ones are when you have the negative exponents. Remember, negative exponents don't make your answer negative. They cause a reciprocal. So 2 to the power of negative 2, remember, means 1 over 2 squared, which is 1/4. 2 to the power of negative 1 is 1 over 2 to the power of 1, which is 1/2. So those are some of your properties of exponents. And remember, any base to the power of 0 is always equal to 1. So here's our coordinates, and we get a graph that looks something like this. So these are the types of functions we're going to be working with today. So exponential functions, by definition, is a function in the form of f of x equals b to the power of x. So notice that our x value is in the exponent. That's why we call it an exponential function. Where b is always a positive number, that's really important. B is a positive number that is not 1. So there are two types of exponential functions that we work with. There's exponential growth, which occurs when your b value, that base, is greater than 1. So here's an example. This was from our warm-up, like 2 to the power of x. Notice our base is bigger than 1. And what you'll get is a graph that increases as we move to the right. And then the other type is exponential decay, and that happens when b is less than 1. But remember, b is always positive, so between 0 and 1. So here's what the graph of 1/2 to the power of x looks like. So notice instead of increasing, it's going to be decreasing. However, they do look very similar. They're actually reflected. So all exponential functions have horizontal asymptotes. So an asymptote is a line that a graph will approach, or it will get really, really close to, but it will never quite reach. So for our parent functions, for these exponential functions, they have horizontal asymptotes at y equals 0. So you can see if I draw in the line y equals 0, which is just a horizontal line at 0, you can see that both of our functions get really, really close to that line, but never quite reach it. Now, of course, this could change if our graph is shifted up or down, but for the parent functions, that's where our asymptote will start. All right, so let's try graphing some of these exponential functions using transformations, and then we're going to define the domain, range, and the asymptote. All right, let's look at this first one. So first, we can start by graphing or doing a quick sketch of our parent function. So our parent function is the function without any transformation. So in this case, our parent function would be base 3 to the power of x. So the 2 is going to be a transformation, and so is that minus 1. So let's start by graphing our parent function. So we know that 3 to the power of negative 2 would be 1/9. So it's a really, really small number, so something around here. We know that 3 to the power of negative 1 is 1/3, so a really small number as well. Anything to the power of 0 is 1. 3 to the power of 1 is 3. And 3 to the power of 2, or 3 squared, is 9. So 3, 6, 9. So this is our parent function. I'll do it as a dotted blue line, and I'll label it P of x. So now let's look at the transformations we see. So the first one we should address, because it is multiplication, we always do those first, is this 2. So this 2 out front causes a vertical stretch by a factor of 2. So that means we're going to take all of our y values and essentially double them because they're going twice as high. So for these first ones, I mean, they're not going to change significantly, but this y value of 1 is going to double to 2. This y value of 3, we double it to 6. And you could double 9, it's going to go way off our graph, so I'll leave it off. And then this red is our intermediate step. So it's going to look something like this. So that's our vertical stretch by a factor of 2. And then we need to address our last transformation, which we can see here in green. I'll highlight it in green. This minus 1, since it's next to the x and it's subtraction, we know this is actually going to shift or translate our graph to the right 1. So you could take all the points that we just found and we move them to the right 1. So that first point will shift to the right 1, second one shifts to the right 1, this is going to shift to the right 1, and this is going to shift to the right 1. So our final graph is here in green. So we can label that f of x. So again, just remember we should always address transformations that involve multiplication before addition or subtraction. So we have to do the vertical stretch first and then shift our graph to the right 1. Okay, now that we have our graph, let's see if we can look at the domain and range. So you can see that our domain is going to be all real numbers because our graph is going to keep heading to the left infinitely and a little bit to the right infinitely. Although it looks like it's mostly going up, it is going a little bit to the right. So our domain is all real numbers, and we'll do that in interval notation. So negative infinity to positive infinity. We can see that our range is everything above 0 because we do have that asymptote. So you can see our graph gets really close to 0 but not quite. So we're going to do parenthesis 0 because it never hit 0 to positive infinity. And then our asymptote will be that horizontal line at y equals 0 because our graph was not shifted up or down. So the equation of our asymptote is y equals 0. All right, let's look at example B. So here we do have a transformation, but let's start with our parent function. So p of x, it would just be 1/2 to the power of x. So this is exponential decay because that base is less than 1. So let's see if we can plot a couple of points here. So let's try plugging in. So if we do 1/2 to the power of -2, remember that causes a reciprocal because it's a negative exponent. It actually means 2 to the power of 2. So notice this 2 goes from the denominator to the numerator, and then the exponent is positive. So 1/2 to the power of -2 is actually 4. So we have -2, 4. 1/2 to the power of -1 is actually just 2. So remember the 2 flips to the top, so 2 to the power of 1. So we have -1, 2. Anything to the power of 0 is 1. 1/2 to the power of 1 is 1/2. 1/2 squared is 1/4. So you can see that it does have that decay feature where it slowly is going down. Okay, so now that we have our parent function, we can address the transformation that we see. So I see here in red we have that negative out front. So remember this is a reflection and it goes over the x-axis. It is a vertical reflection. So essentially all of your points move the same distance from the x-axis, but now we're going to move it to the bottom instead of the top. So this one goes 4 units below, 2 units below, 1 unit below, 1/2 a unit, and 1/4 of a unit. So it looks like this. All right, so looking at the domain and range, again, our domain is going to be all real numbers. But you can see that this time our range is everything below 0. So remember, we always do lowest to highest. So our lowest value is -infinity, and our highest value is 0, but it's not included. And since our graph did not shift up or down, we still have that horizontal asymptote at y equals 0. So that did not change. All right, and let's look at this last example. So again, we are going to start with our parent function, which in this case is just base 2 to the power of x, and then we'll address the transformations after. So we've already plotted this graph a couple times now. So we have -2, 1/4, -1, 1/2, 0, 1, 1, 2, 2, 4, and 3, 8, because 2 cubed is 8. This is from our warm-up. So let's see, 2, 4, 6, 8 right there. So it looks like this. This is our parent function, p of x. All right, and so now we can address our transformation. So I see two transformations, and we can actually do them both at the same time because they're both shifts. So if you look here, this +4, since it's grouped with the x value, it's going to be horizontal, so that shifts our graph, remember, to the left 4. Remember, that always moves in the opposite direction. And then this -3, it's not grouped with the x, so it must be vertical. And this is actually going to shift our graph down 3. So all of our points are going to go left 4, down 3. So we can start here if we want. So we go 1, 2, 3, 4, 1, 2, 3, and we plot our point. And we could take that next point, go left 4, down 3, and then our next point moving to the left, so left 4, down 3, left 4, down 3, and then you can kind of, do your best to estimate the other ones. Left 4, down 3, left 4, down 3. So you get something like this. So you'll notice that since our graph has shifted down 3, we now have a new line that our graph is approaching. So we have a new asymptote, and it's right here. This is our asymptote at y equals -3. So it's no coincidence that our graph shifted down 3, and so did our asymptote. That will always occur. So the only time our horizontal asymptote will change is when we have a vertical shift up or down. So the domain of f of x of our function is still all real numbers. For our range, again, you can see it's everything -3 and above, but it doesn't include -3. And then again, our horizontal asymptote is at y equals -3. So there you go. So you can see how, again, we can use transformations to help us graph our functions. So now we're going to talk about one way that we can start learning how to model with exponential functions. And this is how we can model something that has a constant % increase or decrease, which is a really common scenario in real life. So we can use this model, f of t equals a times 1 plus or minus r, depending on the scenario, to the power of t. So this is going to be our model where a is always going to be greater than 0. Okay, t is the time in years, so you can say t represents the time in years that has gone by. R is the constant % increase or decrease, and that's written as a decimal, and we call that the growth or decay rate. And then this 1 plus or minus r, that total value, whatever that comes out to be, we call that the growth or decay factor. So we can use this to help us model something that is increasing or decreasing at a constant percentage. Okay, let's try this one together. Tony purchased a rare guitar in the year 2000 for $12,000. Experts estimate that its value will increase by 14% per year. How much will the guitar be worth in 8 years? So remember, we're going to be using the model f of t equals a times 1 plus or minus r to the power of t. So first we need to start by making the model. To make the model, we need to find the a and the r value. So the r value we are given, we can see it's right here, it's 14%, but we need to make sure to write it as a decimal. So remember, 14% as a decimal is 0.14. You move your decimal point over 2 spaces to the left. So since it's increasing, we're going to do 1 plus 0.14. So that gives us f of t equals a times 1.14 to the power of t. So now we still need to figure out what this a value is. And we can do that by looking at this initial purchase rate. So when he purchased it, right, that's when t equals 0. So again, when he purchased, so in the year 2000, that was when t equals 0, because the time just started. And we know that the value of the guitar, so f of 0, which models the value, was $12,000. So we can substitute that into our equation. So again, the value was $12,000 equals a times 1.14, and that occurred when t was 0. So t equals 0. Anything to the power of 0 is 1, so that means that a is equal to 12,000. So you guys are going to see that in this formula, a is actually going to always be the initial value of your investment or your purchase. Okay, so we can kind of use that for future models. But of course, you can always just plug in a point that you know to help you find a. So our function is f of t equals a, which is 12,000, times 1.14 to the power of t. So this is our model. So using this model, we can figure out for any given time in years, that's our input. We say how many years has Tony owned the guitar. Our y value, or our output right here, is going to be the value of the guitar. So this function again tells us the increased value as time goes by. So they were asking, how much will the guitar be worth in 8 years? So they're essentially asking us to find f of 8. So we do 12,000 times 1.14 to the power of 8. Now here we can use our calculator to help us get a decimal approximation. Your calculator will always follow order of operations, so you can actually type it in exactly as you see it, which is what I would recommend doing. However, if you don't do that, please make sure you're following order of operations and that you're raising 1.14 to the power of 8 first, then multiplying by 12,000. You cannot multiply 12,000 to 1.14 and then raise it to the power of 8. So again, you can type it in exactly as you see it like this, and your calculator will follow order of operations. So f of 8, you should end up with 34,231, and we're going to round to the nearest hundredths because it is money. So we'll say 0.04. It was 0.037, but we'll round up. So that means that in 8 years, the guitar will be worth $34,231.04. So pretty good investment. All right, so let's try one more together. This one says the value of a truck, sorry, this was supposed to say truck, a car, purchased new for $28,000, decreases by 9.5% each year. Model this scenario with an exponential function. So we'll start with that. So again, we're going to be using our model. So f of t gives you the value given time in years gone by. So we do a times 1 plus or minus r to the power of t. So in this case, our r value, since it says it decreases by 9.5, we're going to do minus our r value. And 9.5% translates to 0.095 as a decimal. So remember, you simply move your decimal point over 2 spaces to the left. So remember we have to do 1 minus 0.95 because it's decreasing by that percentage. And then our a value, well, let me put that in parentheses first. So 1 minus our r value gives us 0.905 to the power of t. Remember that A value is always going to be the initial value of our investment or purchase. So that A value is 28,000. And here is our model. So just so we can interpret again what this model is telling us, this model will tell us the output is the worth of the car, or the value of the truck, given time in years gone by. Okay, so here, now that we have our model, it says then find after how many years will the value of the truck be $5,000. So this time we're actually solving for t, because they say after how many years. And they're telling us that the value of the truck, the final worth of the truck, is $5,000. So for this one, we haven't yet learned how to solve exponential equations, so how to solve for this. So we're actually going to use Desmos to help us find this answer. So they're essentially asking, what is the x value when the y value is 5,000, right? F of t is 5,000, and they want us to find t, which represents our x value. So we can actually put this function into Desmos, and it will give us a graph. And then we can look at our graph, and we can kind of estimate pretty close to see what the x value is, how many years have gone by when the y value has reached 5,000. So let's see what this graph looks like. Okay, so here's what it would look like if you type your function into Desmos. So here we have the model that we created. And remember, the question that we're trying to answer is, what is the x value when the y value is 5,000? So you will need to really zoom in to where your y value is 5,000. And then on Desmos, you can actually trace along your line. So you can take your cursor and you can go along your line, and you can kind of try to get really, really close to 5,000. It will be hard to get it perfect, but again, we're just doing like a rough estimate. So here you can see that I traced along and I got the point 17.253, comma, a little more than 5,000. So this is actually a pretty good estimate. So it's about 17 years. So again, you kind of use Desmos, you trace along till you're really close to when y is 5,000, and you get that your x value, your input, was really close to 17. So we can say that it would take approximately about 17 years for the truck to be worth $5,000. And again, here we're just doing a rough estimate based on the points that we found on Desmos. Alright, so here I have two for you to try on your own, so please pause the video and give these a try. It is important that you do these on your own to see how much you understand. And then we will check your answers in just a few moments. And for part B, you can use Desmos to help you find your answer. Okay, go ahead and check your work here. So for the first one, your A value is 800, your R value is 0.27, and since it's decreasing, you are going to do 1 minus 0.27, which is why this value, your growth or your decay factor is 0.73. So here's our model. So here they want to know how much will the computer be worth if she wants to sell it after 5 years. So we're essentially finding f of 5, and you should get 165.85. So make sure we round to the hundreds because it is money, and that's how we round money. For the second one, our A value is 5,000. Our R value is 0.0325. And since it's increasing, we do add it to 1. So you can see our growth factor is 1.0325. So here's our function. And they're saying how many years will it take for the account to be worth $10,000. So they're essentially saying find X, or your input, when Y is 10,000. So you can see here I plugged it into Desmos. Here's our function. Remember, zoom in really close to when y is 10,000 and use that trace feature. And you can see I got really close to y equals 10,000. It was hard to get right there. And you can see that our y value is pretty close to 22. So if we rounded to the nearest whole year, it'd be 22. So we could say it would take approximately 22 years. Okay, that is all for today's video. Thank you so much for watching.